So yeah, good morning everyone. So for our first talk today we have Felipe Espreafico from Sorbonne University talking about motivic and arithmetic refinements of Donaldson-Thomas Invariants.
Thank you. Thanks to the organizers for the invitation. I'm very happy to be in Miami. It's actually my first time here and also my first time in the US with the experience. So I'll talk about the motivic and arithmetic refinements. So just to clarify some things, singularity theory is not my main area, let's say. I work with like slightly different things, but mainly real Gromov-Witten theory and enumerative geometry. So I'll start by explaining what I want to mean by this refinement. And for that, I want to make a little detour about enumerative geometry. So I spend, I don't know, 20 minutes, maybe 30 minutes on enumerative geometry things, and then I'll explain how to apply these things to this Donaldson-Thomas invariant and how this relates to singularities and Milnor fibrations, which I guess is the main topic. So part of what I will say is joint work with Johannes Walcher, part is joint work with Stefan McKean and Sabrina Pauli. But, well, I'll mention the names of the people one sec. So this is basically the outline. So the first three things are more like enumerative geometry, and then I'll try to explain how to apply this to get this refinement. So, well, enumerative geometry is just concerned about counting geometric objects satisfying some restrictions and properties. So one of the simplest questions we could ask is, for example, how many conics pass through 5 points? This is a very simple question that probably everybody has seen at some point in their life. The only thing that we have to be careful about this type of question is that when we say 5 points, it can't be any 5 points. We usually are interested in a generic situation, because if we just have 5 points, if we take 5 points in a line, you have an infinite number of conics, and the question doesn't even make sense. So we need usually, not, I mean, depends on exactly the thing, but usually we are interested in the generic case. So we want generic configuration. And we also want to first make sure that we expect a finite answer, which means a dimension count. So how do we solve this problem about the conics? Well, the idea is that a conic in P2, for example, is just an equation of degree 2, something like this. I'll write all the coefficients. So here we have 6 coefficients, so this is a P5, and then we are just, the 5 points will be 5 equations in P5, and then that's why we expect a finite answer. And since the points give equations of degree 1, the answer is only 1 conic. And this is like a general idea that we use to solve this problem. So we first consider some kind of moduli space for the object we want to count, here plain conics. So we get a P5, but in general, it's going to be more complicated object. And then we consider its cohomology, usually Chow cohomology if we are working in algebraic geometry, but we can also consider other types of cohomology theories. And then the subvarieties, the restrictions become subvarieties in this moduli space. Like here, the points, which are the restrictions, become degree 1 equations, degree 1 curves here in P5. And then we just compute the intersection in cohomology. This should be a 0-dimensional set if we want a finite answer. And in the end, we just compute the degree of the class we got. So this is how you kind of solve these problems in general. Of course, I'm being very simplifying many things, but that's the main idea. So now I want to kind of continue this kind of detour on enumerative geometry by using two problems as main examples. So the first problem is this problem of counting lines on hypersurfaces. So the question is, how many lines are there on a generic hypersurface of degree 2n minus 1 and n plus 1? So the main example, again, is n equals 2, where you get the cubic surface that has 27 lines. Everybody has heard about this. So here, this modular space will be the Grassmannian of lines in Pn plus 1, which has dimension 2n. And the way you compute this, this class related to this hypersurface, which is the condition the lines have to satisfy, because they're counting lines, and what is the condition? Is that the lines are here. The way you do this is that you consider this vector bundle. So you take the tautological bundle, and then you consider the symmetric power. So basically, you are looking at polynomials on each line of degree 2n minus 1, and basically a general section of, and you can consider a section of this, which is just restricting our hypersurface to the line, to each line. This is a section, and the zeros of this section are exactly the lines that are on the hypersurface. And so the Euler class of this bundle will give you like will correspond to the zeros of a generic section. And this is also rank 2n, so this means that the zeros of a generic section should be a dimensional zero set, and then you can compute the degree. And then we get these numbers 127, 285, and so on. I think these two are very famous. I think most people know these two numbers. Well, one also is very famous, but the others are less. People don't know them, but it's okay. And now another problem that I want to use as an example is this problem of counting rational plane curves. How many rational plane curves go through 3D, go through 3D minus 1 times in Fichou? Well, generic, again, I forgot to write it, but it's generic. And this is basically this problem, but generalized. And this is very famous because this is famous in Gromov-Witten theory. This for solving this, we use the modular space of stable maps of degree 0 and 3D minus 1 points. And the classes are defined from the evaluation maps. So here we have 3D minus 1 marked points. We have a natural evaluation map, and the classes are simply the inverse images from the evaluation map. And they're going to be degree 0. We can just count dimensions, not so complicated. And these are examples of, like, maybe the first examples of Gromov-Witten invariants. Here, it's not so hard to calculate. Like in this first example, these computations are, well, I won't say easy, but they are very doable by Schubert calculus or torus localization, a simple thing. These are a little more complicated, but they were first done by Kontsevich and Manning, and they got a recursion for these numbers that I didn't write here, but these are the first 5, 1, 1, and then 12, 6, 40. But they can also be computed by localization. This is a work by Kontsevich. Yeah, but this is all over C, right? So the goal of this talk is to consider not only the complex numbers, but more general fields. That's what we mean by refinements. I'm gonna get in details soon. But over R, for example, how can we study this problem? Because if you look at these problems, the first thing you can ask is, okay, I want to count lines on a hypersurface, but why doesn't this depend on the hypersurface, right? Why this number is always constant? And the idea behind it is the same of the fundamental theorem of algebra. So you have a polynomial of degree n, it has n roots. And that's basically the same thing that is happening here. You have something defined algebraically, and then it's expected that you have the same number always. But again, the fundamental theorem of algebra needs an algebraically closed field. So if you are over R, then these answers are not invariant anymore. So you have to change the way you count things. So let's talk about the real case, which has been studied classically, and then we're going to explain ideas of how to go to different fields. Because, well, of course you could say, but I can define this Riemannian over any field, this Euler class is defined the Chow group, whatever. But the point is that when you compute the degree, this always gives you an answer that only has meaning in the algebraically closed field. So you're counting answers over C or over your closure. So how do we count things that have some meaning over R? So over R, this problem of lines and hypersurfaces was studied by Steger. This is not I mean, there are two Stegers. This is actually the nephew of the more famous one. This funny thing that it took me a while to understand that. But yeah, so he basically studied what lines appear over R, because of course you have 27 lines. To take a real cubic, you have 27, and well, how many of these 27 lines are real lines? And what he showed that is that there can be 3, 7, 15, or 27 real lines, and you classify the lines in hyperbolic or elliptic by defining an involution. So he basically defined an involution on the line. I don't know if I have time to explain this involution, but the idea is that if you have a cubic and you take a hyperplane, you get something of degree 3 when you intersect with the hyperplane. So if you have a line on the cubic and take a hyperplane through the line, well, the line is going to be part of your curve. And if to get something of degree 3, you need a conic, because you're getting a hyperplane through the line, and you need a conic. And this conic, of course, defines an involution on your line, because it intersects these 2 points. So that's basically the involution he defined. And then he looked at, well, when is this involution, the fixed points of this involution defined over R and over C. So basically it's when, like, you get a fence, because you can vary your plane to get the different involutions, and then, well, you can ask if the fixed points are defined over R or C. And well, he found that if you have 27 real lines, you have 15 elliptic and 12 hyperbolic, 15, 9, 6, this table here. But one thing he apparently didn't notice is that if you compute the difference of these numbers, it's always 3. So this is something that apparently, like, he didn't say in his paper, or maybe he noticed, but it wasn't written anywhere. And only more recently, like in the 2000s, some people noticed that, well, then you can count lines with signs, right? So you can say that elliptic lines are positive and hyperbolic are negative, and now you can have an invariant count, an invariant sign count that tells you something about the geometry of the situation. And well, apart from that, some people, Tinashe, Karlamov, and Okonek and Telemann, studied this problem not only for the cubic but in general. And well, they concluded that this hyperbolic and elliptic interpretation is actually consistent with this idea of taking the Euler class. So since here you have this this fiber bundle, you can still consider this over R, and then you can consider like a sign count there. I mean, by looking at the orientations, the local orientation. So each intersection with the 0 section will give you a plus or a minus. And this interpretation here is consistent, so they give the same result. Of course, it's not so easy to tell you when you can compute the degree. You have orientability conditions that you have to satisfy, but let's not get into that. And here the sign counts are always 2n minus 1, so the double factorial. By this I mean only the odd numbers, to multiply the odd number. And this is a very nice thing. And About the rational plane curve, this is the so-called Behrend invariant. So this is a little more complicated. But for d equals 3, for example, you can have 12, 10, or 8 real curves. You can also consider here the situation where the points are not real. You can get all real points, and then you have this situation, but you could also consider that you have real points and complex conjugate points. And then you get different invariants. And here the sign count that you consider is the number of elliptic nodes on your curve. So your curve is rational, so it has nodes of singularities, and then it can have either elliptic nodes, which are defined over C, and real nodes, which are, so basically this, this thing, and this thing. And well, they count only the elliptic ones. And then these numbers were actually computed through tropical geometry. So I don't know if there's a direct method to compute these numbers without this tropical idea. And yeah, so these are the first ones, 1, 1 again, because these are just linear algebra, so they're going to be the same always. But then 8 and 240 and so on. Right. So now, what about other fields? So let's discuss a little bit how can we generalize these ideas to other fields. So basically, well, this enumerative invariant, so basically you have a moduli space or something, and you associate a number, and it's counting something. So a refinement that the thing we want to do, so is to basically consider counts which are not necessarily numbers, but something in some ring that refine this number. So you can get something here, and then you can go back to Z and get the original. So that's what we're going to do. We're going to go to a different ring and then go back to Z. And in our case, we want something that kind of refines this idea that we have invariance over C and over R. And we want something that helps us refining both of them. So encodes all the counts over R and C, and actually over other fields as well. So this is basically the origin of this field called quadratic enumerative geometry or arithmetic enumerative geometry or A1, and there are many names. But I like quadratic because we use quadratic forms to count. So basically the idea is that, well, over C, we are simply counting the number of zeros of either a generic section of a bundle or an intersection of classes, things like that. Over R, as we saw, we have to consider sign counts, and the sign counts are related to this local orientations on the moduli space, and usually some geometric condition that we saw. So for example, here we have an involution, which is geometric, and we look at properties of this involution. This is also related to this local orientation. And in general, but now if we want to consider other fields, the contributions are not going to be only sign, but square classes. So instead of -1 and 1, you're going to have square classes, and when you sum them up, you get quadratic form. Because of course, a quadratic form up to isometry is just a bunch of square classes. And so we have to consider, and so I'll explain soon how you, for these examples, these quadratic forms appear. But let me first define this ring, the ring of quadratic form. So basically, so the isometry classes of these pairs, V is a vector space, Q is a quadratic form. You can sum two quadratic forms by considering the direct sum. You can multiply by considering the tensor product. And then you define this ring by basically adding additive inverse. Because of course, this has no inverse with some operation. So you need to add artificially some minus object. And this ring is going to be generated by this classes A, which is just A times x squared. So basically, that's because you can diagonalize quadratic form. So if you have a quadratic form, you diagonalize, and then this is just sums of this one-dimensional quadratic form. And of course, A has to be a square class. And you have a rank morphism, which computes the dimension of this. And if your field is inside R, you can look at the signature, which is just the number of minus and pluses in the diagonal. In our case, actually, it's not it's the difference between minus and plus. That's what we are going to consider. And I also want to define this, which is a little more involved. I don't want to get into the technical details, but basically you can also define a shell group theory using this quadratic form. So we can do cohomology theory. There are many ways of doing this, but the main one is the Milnor K-shifts. Maybe you've seen this for the classic shell group. You have Milnor K theory, and you can define the shell group as a cohomology of this K-sheaf. I won't define what it is here, but basically here you consider a similar sheaf, and for that, and then using this, you can define these groups by a cohomology of this. L here is a vector, a line bundle, sorry. And well, the properties are that for the point, you get the Grothendieck bit, like for the classic, you get C. You have pullbacks and push forwards. The important thing is that for the push forward, you need to consider this determinant bundle here, this relative determinant bundle. And this is related to orientation. So it's the same thing over R. To compute this degree, you need some orientation, and this is basically what's happening here. So in the end, you have a degree map from the like N class N group to GW, but you need to have a map on the group twisted by the determinant bundle. So again, this is related to orientation. And in the end, here you also you can define an Euler class here by pushing forward and here is if you want to define an Euler class of the bundle, like an Euler class of the tangent bundle, of a vector bundle, yeah. You have a vector bundle, you have the determinant of the vector bundle, and then you can define an Euler class here. So it's not only in the on X, it's always twisted by the determinant bundle. That's what I wanted to say. Sorry.
Can you remind me, does this group fit in a Tate diagram?
Which group?
Grothendieck ring.
Yeah.
Does it fit in a Tate diagram?
What do you mean by a Tate diagram? Okay.
I can comment.
Yeah, so let me go back to the examples now and explain how do we see this in practice. So basically, now we go back to this involution, and here in these involutions we have, well, it's an involution, so it's the fixed locus is actually defined on a quadratic extension. The same way as over R you have C minus C and R. Here you have a quadratic extension just because it's an involution, it's a degree 2 thing. And well, now you just look, okay, in which extension this fixed locus is defined, and it's going to be something like K of alpha, and alpha is going to be a square class because it's a quadratic extension. And this is going to be the contribution. Well, I'm lying a little bit because you can have lines that are not defined over the base field. So the involution is going to be a quadratic extension of the field of definition of the line. And then you have to take the trace if you want to go back to your base field. But this is the basic idea. And one thing that I did with McKean and Pauli was to show that this interpretation agrees with the Euler class computation. So if we go to these groups here, and we compute this Euler class, we're going to get a degree here. And what we showed, and like you're going to get local contributions because so the degree is just the sum of all these local quadratic contributions. And what we showed is that this interpretation using involution is the same as this Euler class in general. This is recent work. Oh, for n equals 2, this was actually done before by Krefl and Walcher. And it's also easy to compute the general count. So this is about the local contribution, but then when you sum them up, you get something, for example, for n equals 2, you get something like this, 15 ones and 12 minus 1. So it's basically a quadratic form with 15 pluses and then 12 minus, something like that. And oh, sorry. And then the cool thing is that it actually works for any field that you consider. So basically, even though you have contributions that are not like 1 and minus 1, when you sum them up, you get something in terms of this 1 and minus 1. And then you can recover real and complex if you just compute rank and sigma. And of course, you can also do the same for the other ends. And it's always the same. It's always 1 and minus 1. And it makes sense because if it's something that doesn't depend on any field, it has to be something in terms of 1 and minus 1.
What's the hypothesis?
For n equals 2, it's the cubic.
Oh, that's the 27.
Yeah, the 27. Yeah. So if you sum these two numbers, okay. But of course, for other hypersurfaces, it's different, but it's always the same thing. You just subtract and give you the real count and stuff. For rational plane curves, this was also considered by this work in Levine, Solomon, and Behrend. And basically, the nodes are now defined again over a quadratic extension, so it's a similar idea. And then you get this, for each node, you get a contribution. And then instead of just counting the elliptic nodes and taking the minus 1, here you have to multiply the norms of each A alpha I. So it's the same thing that it was done over R. Elliptic nodes are defined over C, so it's a minus 1 here. And then you just multiply the minus 1. But here, of course, you have more different quadratic extensions, and the contribution is that. But again, if you just sum them up, then you get combinations of real and complex like this. But if you consider non-rational points, so if you begin with real points and complex conjugate points, sorry, not real, but rational, and then points that are depending on an extension, then you're going to get things that are not depending on 1 and minus 1. Because, of course, your points depend on the field that you are choosing. So it makes sense that this comes will depend on. So basically, that's what I was mentioning. So I won't be very precise here, but basically, you can show that in many situations, these counts don't depend on the field. So basically, you can kind of evaluate something in terms of these 1s and minus 1s, and this won't, the count won't depend on the field. And then you can take rank and signature, recover C and R. So let's now, after this, so after this, the tour to enumerative geometry, now that we have an idea of how this quadratic counts work, I want to show how to apply this to get refinements of Donaldson-Thomas. This is one possibility. There are some other things. In the end, I'll mention some other work that's done different refinements of Donaldson-Thomas Invariants. So this is one possibility, and it relies on this Behrend theory, this Behrend's idea. So now this part is joint work with Johannes Walcher, this part that I'm going to talk about now. Okay. So basically, Donaldson-Thomas invariants are just, so here I'm introducing them as counts of ideal sheaves on Calabi-Yau-Tree. So this actually can be, in the end, counts on any type of moduloid space, but here I'm focusing on Calabi-Yau-Tree codes. And then we just consider, well, we have a subscheme V. So here it should be V, sorry, why, but it should be V. And then you have a fixed homology class, and then you can have a moduloid space that counts ideal sheaves with fixed homology class and fixed Euler characteristics. Again, it should be V. And well, you can using obstruction theory, perfect obstruction theory, you can define these virtual classes and compute the invariant as the simple integrals. So basically, you have some kind of modular space. You can define these virtual classes and compute this number that is called Donaldson-Thomas invariant. And what Behrend showed is that these types of invariants defined this way do not depend on the obstruction theory you choose, only on the scheme structure. And to do this, he basically constructed this constructible function, Vz, mu z, and so z here is our modular space, and he showed that this invariant can be computed in terms of topological Euler characteristics of some sets, so the inverse images of this function. And well, for smooth points, this function is just a sign. So basically, if you have a smooth space, this is just going to be the Euler characteristic. But times the sign. And now if you have a critical locus, so take a function, a smooth morphism on a smooth scheme, and now you define this z as a critical locus. So suppose you can write your modular space as a critical locus, which is very common in physics, which is Chern-Simon's theory, for example. Then the Behrend function is going to be given as this. So 1 minus the Euler characteristic of the Milnor fiber times the time. So this is now where the singularity starts to appear. But this is all over C, the situation. And now we want to consider refinements like the ones we consider. So how we can consider refinements of this? So first we need to consider motivic virtual class. So basically we're gonna substitute the Milnor fiber by something more refined, let's say, which is something in this Grothendieck ring of varieties. This is also a classical thing, and it was already mentioned, I think, in previous talks. So you can consider this ring of varieties here, which is basically some kind of universal Euler characteristic. So you have spaces, and you have this relation, which is cut and paste. You have this product. So the product is just the Cartesian product. The affine line is denoted by L. And you can also consider an equivariant version of this ring. So this is the ring of varieties. You can also consider an equivariant version using group action. In our case, the most important one is going to be the roots of unity. So this is the profinite limit of the group of roots of unity. And then you can localize this L to the -2 here, because it's going to be important in the next slide. And so the idea that we're going to use in our situation is the following. So we have this, if we have a projective variety, we can consider the Euler class of the tangent bundle. And this, as we said in the beginning, we can compute degrees of Euler classes and everything. So we have a degree map in GW. So this gives you a refinement of an Euler characteristic. So we can compute A1 or arithmetic Euler characteristic in this ring. So this is something that we can do. Okay, even though it's just for projective varieties, there is a result by Wittner that says that this ring is generated by such varieties. So we only need to deal with this case. And this gives us a refinement of the Euler characteristic. And since we have to localize this thing, we also need this alpha here. And now, how do we make our refinements? We consider this very famous story by Denef and Loser, where they define this motivic Milnor Fibre, so or motivic zeta function, and then the Milnor Fibre is the limit. So basically, if you have a critical locus, you can okay, I'll define this first, and then I'll go back to that definition. The order should be reversed. So if you have a critical locus, you basically can solve the singularities of the zero part, and you have something like this. And now, when you consider the simple normal crossing divisors on the resolution, you can basically consider all of them here and either multiplicities. You can look at the intersections, and then you can remove the unions of the other intersections with the guys that are not there. And then you can take a covering space depending on the multiplicity. So basically it's the GCD of all multiplicities. And this gives you a class in this equivariant ring here. And this is basically already the limit of the zeta function that is defined in Denef and Loser's work. And here you can then define a virtual class by basically using this idea here. So we have something that we defined for the Donaldson-Thomas invariant. So we basically switch this Euler characteristic of the Milnor Fibre by this SF. This was already appearing in Behrend, Bryan and Szendroi work, and we basically now consider the refinement of this to the Grothendieck-Witt ring. And the main example we consider is the invariance of A3. So for A3, we have the Hilbert scheme of points. And here, because remember, so we want to consider ideal sheaves of, in this case, we want to do degree 0, so Euler characteristic 0, so points. And we have, not Euler characteristic 0, but dimension 0, so points. And then the Euler characteristic is the number of points. So we're going to consider something in the Hilbert scheme. I have 10 minutes? Yeah, that's going to be. So here, so these are the ideals that have dimension n when you quotient this, and so I'm just gonna show how do you see this as a critical locus very quickly. So this is something that I think, it's very classical, but also very nice. This goes back to Nakajima, or even before. But basically, the idea is that you fix a vector space of dimension n, which is gonna be this quotient. You fix an action of the polynomials in this space. In the end, and you fix an element that generates the whole space. So, we're gonna call 1. So now, if you, so this is what gives you this vector space of this form. So basically, the idea is that you have these matrices, which are the action of this guy, and you have a point here, so it's something in this space. And the matrices have to commute, because of course you want something in the polynomial ring, and you want the points here to generate Gn, which are these 1. And of course you have to quotient by this GLN, because, it depends on the base. So basically you can consider the following thing. You just consider this manifold here, without this condition of commutativity. This is going to be smooth. And then you just define this map, which is computing the trace. And when you take the derivative of this map, the derivative is 0 exactly when you have the commutative. But here you need r equals 3. If you try to do this for higher n, this is not going to work as nicely. So for the Hilbert scheme, and in our case, we are mostly interested in this dimensional 3 case. And so you can consider this. And then Behrend, Bryan and Szendroi, they computed some refinement using this ideas. And well, we can have the refinement of this.
Sorry, what is B then? B sub M.
Sorry, it's just this vector. It's just a vector space of dimension n. So we fix a vector space of dimension n.
You vary the field.
Yeah. So for this you can do over any this works over any field. Like also this is just these things work over any field.
What does it mean B generates?
Yeah, well, because you have an action. So so here, so this is the the thing. So you have an action. So the space is basically A1. So you have matrices here and this V. So you have an action of these matrices on the space, and you want that V generates in the sense that if you apply the action on V, you can get the whole space. Basically, the idea is that if you are looking at this Hilbert scheme,
And you get a spanning set.
exactly, because you need a one in this space. So because what is the quotient of a polynomial ring? It's just a vector space of finite dimension with an action of R elements, and you need a one. So this is basically what you're doing here. And now when you do this, you get well, here it's just with three matrices, and and then when you have this, the idea that you use is that you can compute the Milnor fibers by basically looking at the generic fiber of this map and the zero fiber of this map, and do some computations. It's not so simple. But
So Z fully depends on the function. The Z that was defined. Z, yeah.
You mean this function?
Yeah.
Like the thing is that yes, but this function is just this one.
Yeah, I know, but I mean, if you want to do this in like for higher R.
Yeah, for higher R, the problem is that this function won't give you the Hilbert scheme as a critical locus. So that's the point. For R equals 3, this function has this nice property that when you take the derivative, you get exactly the commutator. And in general, you won't get that. You get something different. And then you can't just apply the same idea. But we can refine this to this Grothendieck bit. And the nice thing is that now, if we take the real, like the signature of this, so we consider this over R, we get, okay, I didn't say that. So this function here, so if we take the rank, now for this refinement, so if we take the rank, we get something over C. This is the so-called McMahon function that counts plane partition. So this is this function here. I think it's something like 1 minus e to the m to the minus m. Hopefully it's right. Yeah. So this function counts plane partition. So it's the generating function of plane partition. Maybe you've seen this once in your life. So it counts these types of diagrams here. So consider that you have some kind of edge here, and so on like a room, and then you are putting boxes here. So you have boxes like this. And now we want to count how many ways you can put n boxes on the corner of the room without them, of course, falling. So you don't want to put a box here flying, so it will fall. So, for example, this is for 4 boxes. This is one way, but you could put this thing here, and they all have to touch. You could put it on the other side. You could put it here. So you have many ways of doing this, and this is the generating function of this types of counts. And if you consider the real refinement, the real function is the count of symmetric configuration. So it's the symmetric ways of putting the boxes. So this was already, and I think that's the most interesting thing in our work. This was already computed in physics. So the physicists had already an idea of what should be the real refinement of this work. And the nice thing is that when we did this refinement, we got similar things. And now let me just use my last 5 minutes to
What if you present the Hilbert scheme as the critical locus of some other function?
yeah. So sorry?
What if you present your Hilbert scheme as the critical locus of some other function?
No, this is more classical. Sorry, I don't.
What if you change it?
I want
Change the
to
function.
change the function. We use a different function.
Use a different space and a different function. And then so that your critical locus is still the Hilbert scheme.
Yeah,
So
so
you get the same thing.
you should get the same thing because this Donaldson-Thomas invariant should only depend on the scheme structure of the critical locus and not on the
Represented.
representation. But this is the work of Behrend. But I haven't tried this. I mean, the work of Behrend actually is over C. So because that's what I'm gonna say now about this refinement. We are refining one side of the Behrend work, but there's also a way to refine the other side. So I'll mention this now. So maybe overall,
What do you mean by the sign?
I'll explain. So maybe this could be different over other fields, but I think it should be the same. But let me just say what I mean. So, so basically the idea, so since I mentioned this, let me explain this first. When we do look at Behrend's work, he associated this invariant with this other characteristic of this constructible function. And the point is that we don't have this in general. So for a critical locus, for example, we show that the function is given by this. So what we did is that we took this and we refined this equation. But because we didn't want to construct directly a virtual class in the group in the shall-bit groups that we mentioned. So we didn't look at this class directly, we just refined this other side. So we don't have a direct relation between the virtual class and this Euler characteristic. But there is a refinement of this virtual class that was done by Mark Levine. So he actually constructed a class in that shall group over the Grothendieck bit ring over the quadratic form, this shall bit group. And it's not clear whether this refinement, so we don't have a Behrend function in this context. So this is an open problem to construct a Behrend function. This is something I'm working in progress with Ran Azouri. We actually have some ideas on how to maybe construct such function. But so let me just explain also how this is related to this Milnor number, because you can also consider arithmetic refinements of Milnor number. So basically, it's the same idea as always. If you have you consider a critical function, you consider the derivative. This gives you a map from an to an, and then you look at for each point in the inverse image, the contribution is the square class of the determinant. So you have the Hessian determinant. You look at the square class, you have a quadratic form that refines the Milnor number. And classically, this Milnor number is related to this Euler characteristic. And some works show that if you consider this SF, so this motivic Euler characteristic by Denef and Loser, when you have a quasi-homogeneous singularity, you get something like this. So this AJ are the weight, and E is the homogeneous, quasi-homogeneous degree. So it's slightly different from here. Of course, if you are over R, these things are going to be 1 and -1, and you're going to get this, or over C, sorry. But in general, well, it seems like it's a little more complicated, this situation. This is only done, as far as I know, by quasi-homogeneous singularities. Apparently, I'm not sure if this is done in general. So I think this is still like something that has to be done. And there's also another interesting work by Comte and Fichou where they considered real semi-algebraic set. So instead of considering this ring of varieties, they considered a ring of algebraic set or real algebraic set, which had some slightly different in this K0. So that's an interesting word to relate. And right, yeah, I guess that's all I wanted to say. So thank you for that.